Welcome everybody to the seminar of today. The seminar will be about the hydrodynamics of rowing, and the speaker of today is Jerry Westerweel. And Jerry Westerweel, I just introduce him quickly, and then I leave him the stage. He graduated, he got his master degree in applied physics in 1988 at Delft University of Technology, where he also obtained his PhD degree in 1993. He then became a research fellow at the Royal Netherlands Academy of Arts and Science, and worked as a visiting scholar at Stanford University, the California Institute of Technology, and the University of Illinois. In 2001, he was appointed as the Anthony van Professor, I hope I pronounced it properly, I think not, at the Delft University of Technology, and since 2005, he holds the fluid mechanics chair at the Faculty of Mechanical, Maritime, and Material Engineering. His research interests are turbulence, dispersed multiphase flows, microfluidics, biological fluid dynamics, impulsive flows, and the fluid dynamics of sports. He is the co-author of a textbook on particle image velocimetry and one on turbulence. He has been an editor-in-chief for Experiments in Fluids since 2012. It's with great pleasure that I introduced Jerry Westerweel, and Jerry, I leave you the stage.
Okay, thank you. So Anton van Leeuwenhoek was the inventor of the microscope. So I have a replica of one of his microscopes, and he was not a scholar, he was making cloth. And as a hobby, he invented a microscope, and I think he communicated that with the Royal Society. I think 300 letters or something that he wrote, and but he never got a degree or anything. But he basically, okay, I have to switch to my presentation. And he basically described, I think for the first time, spermatozoa. Yeah, he made these little microscopes with magnifications up to 300 times. So it's so in order to be named on a chair after him. Okay, well, I would like to thank the people in Lille to organize this seminar series and to invite me for this presentation. And yeah, because I think we're already more than a year in this pandemic, and it's very good to see faces of people rather than only exchanging things by email. Okay, and today I'm going to talk about work that has been done by my PhD student Ernst-Jan Grift, who graduated last year. Together with students and other PhD students and co-workers, we basically set about the hydrodynamics of rowing, and let me just start with a little bit of a background story. So here, this is one of the co-authors of this presentation, Arnoud Grijdanus. He was sort of one of the top rowers in the Netherlands, and you can see that he does not look very happy on this thing. That's because if you look at, they became in second. Yeah, and if you look at the final race after 2 kilometers, which takes a little bit less than 7 minutes, you can see that he lost with about 700th of a second. So they go about 7 meters a second. So just a few inches was the difference between number 1 and number 2. And number 2 is always the worst position. You can also see, if you look back at the race, that they were basically one of the slowest starters in this competition, and then throughout the race they actually gained in on the ones who were number 1, who were always in front. Yeah, so basically their speed was higher, but they came in second. Yeah, so and one of the things I'll show you later is what they could have done maybe in order to win, to gain that 700th of a second. But after his rowing career, Arnoud was a PhD student in my group. He still is in my group as a co-worker. But Ernst-Jan we hired on a different project. And basically what we wanted to do in this project was to investigate the kinematics of rowing, and mostly in rowing they focus on the forces here on the gate, and they can measure forces on the handle and on the stretcher. But so far it was not really possible to get the forces on the blade, and also how forces are generated and which forces are important. Because if you know this, then you can try to optimize the rowing blade, and then hopefully win the race. And one of the first things we did, because I think probably some of you are rowers or have been rowing, and basically if you sit in a boat, and you move along with the boat, then you use the rowing oar and the blade to push against the water. Yeah, so it just seems as if you're pushing off against the water. So that's when you push, you have to generate drag. And the thing is, we took a recording from a bridge, and so from a fixed location. So that is this movie. So if you see this, well, first of all, you see that the whole motion is limited to a very small area. That was one that we see, and you could also see there were sort of two vortices being generated. And well, looking at this, so the motion is confined to this region, and basically the blade is moving much more in this direction than in this direction. Now I know that some of you in the audience are aerodynamicists, so if you move in this direction to generate a force in this direction, then we call this lift. Yeah, so the idea was, so what's the relative importance of drag and lift with respect to this blade? Yeah, so this is very classical. So maybe if there's some undergrad students among the audience, they may not have seen this movie. But yeah, if we move, if we accelerate and decelerate, in this case an airfoil, we also generate two vortices, namely a start and the stop vortex. And the total amount of momentum is also the total amount of momentum that is given to the airfoil. But you also see that the vortices are moving downwards away from this airfoil. Now, if we go back to that original movie, yes, so now I put a line here indicating also where the blade is basically moving sort of up and down, and we replay the movie. And you basically see that these vortices occur at the left of this line. Yeah, if it would have been drag, yeah, you would basically expect them to be behind the blade as drag. If you move a spoon through a cup of tea, you can see that the vortices are behind the blade, and here they appear to be on the other side of the blade. It's a little bit complicated, but this was sort of a first idea that we had looking at it. So combined with this motion that is perpendicular, the motion of the blade is perpendicular to the motion of the boat. So what is the importance of lift, and how can we influence the lift? Because we only can generate lift once we have generated a start vortex, and we also should generate a stop vortex at the end of the blade motion. So this was our initial interest, and together with the notion that the whole motion of the blade is confined in a relatively small area, we decided to instead of doing measurements in, for example, a towing tank or in a channel, we decided let's replicate this motion using an industrial robot. Yeah, and then the W that was added here in the name was of course a joke. So here you see this motion. This is all submerged. The robot can also move up and down. This is the slow motion, and then you will see it at a little bit higher speed, the motion of the blade. Yeah, so with this robot, it's a 4-axis robot. we can replicate the motion of the blade, but we use a 1:2 scale model of the blade. As we had to do some scaling. And it was really difficult to find a robot that could really do the accelerations combined with the velocities and range to do this. But we sort of got a used robot at a reduced price where we could easily install this. And here's another little intermezzo for those of you who are not really familiar with PIV. This looks like nicely transparent water. We put in there fluorescent tracer particles. Now we switch off the light and we switch on the laser. And oh, I have to hit here, I think. Yeah. We just switch on the laser light, and then you can see that it's filled with nutrient particles. And this is of course filmed through the free surface. We have the camera on the bottom, and we also have light sheets coming from opposite sides, so we don't have any shadows. And so that is what we applied here. So with PIV, we can get a nice view, a planar view. So one thing we did first was to measure do a 3D measurement of the motion of the blade. So here you can see in red positive and blue negative vorticity of the motion of the blade through the water. And here in blue you can see this. Oh, I have to use this one. This tip vortex. And then the blade motion stops. We generate another vortex, and here you can see in red and blue the two counter-rotating vortices that you saw in that other movie taken from the bridge. And what we got from this is that most of the vorticity actually appears to be existing over the height of the blade. So we, from that, we decided in order to increase the number of measurements that we could take to just do a measurement in the mid-plane of the blade. Okay, so then we first wanted to do something more simple. And what you see here is the starting stroke of a rowing team, and you can see that in the starting stroke that the path is not very curved as what we saw before, but this is almost rectilinear. And you could also see that in this case, I don't know if I can repeat this easily. I think now it repeats. You can see that now the vortices appear behind the blade. So this is typically a motion where we have drag. You can see here the vortices are generated behind the blade. Okay, so this was a much simpler motion. And so we first started by investigating a linear accelerating motion of the blade. And what we wanted to investigate is what is the optimal depth of the blade with respect to the water surface. And so we used the following configuration. We did two types of measurements. First, we did a flow visualization where we had like thin platinum wires wrapped around the plate, and instead of a rowing blade, we used this rectangular plate with almost same aspect ratio as a rowing blade, 100 by 200 millimeters, just in a scale 1:2. And we did some hydrogen bubble visualization. So we put a big anode over here, and then hydrogen bubbles were generated basically at the surface of the plate. So this was to visualize the starting vortices and see where fluid that passes along the blade, where it went. And then following that, we took some measurements with a light sheet. So that's shown in this lower panel. So the plane of the light sheet is parallel to the bottom wall. And then below, we have a mirror and a high-speed PIV camera, so that we can see the motion of the fluid around the plate. This was now a transparent plate, so we didn't have to get the light sheet from both sides of the blade. Yeah, so we just one side of the light sheet was enough. And so we could do accelerations up to well 1.6 meters per second squared with this robot, and we selected a range of velocities up to 0.4 meters a second. That is lower than what is done with the actual rowing, but yeah, by doing this in steps, we could see if it would become independent of the, let's say, Reynolds number. It's a little bit difficult in such a situation with a free surface to define an exact fruit number. So if we computed fruit number 1 for the highest velocity, to what length would it correspond, and we get to 9 millimeters. So basically all dimensions here are much larger than this 9 millimeters. So we assume that the fruit number everywhere was much smaller than 1, so that the surface wave did not really have a contribution. You will also see that later in the visualization. Okay, so let's first start with this hydrogen bubble visualization. So now the plate starts. On the right, you see the actual measured force. And you can see here on top the water surface, which now sort of like goes down. You generate a vortex which is attached to the water surface. This is one vortex. Here there's another one. And this is also 20 millimeters below the water surface. And now we reach approximately the constant velocity that we also see in the starting stroke. And you can basically see there's not many waves generated. So also in the actual stroke, you can see some disturbance of the water surface, but you're not really generating any critical wave that would contribute to wave drag in this case. And yeah, so then we have one set where we have a more or less constant velocity, and then we stop the plate. Actually, what I could not have shown here is that this robot has a very high degree of repeatability, and we could actually start 2 runs with the hydrogen bubble visualization and basically see exactly the same vortices being generated. It seems as if you look at 2 times the same image, but that's not the case. These were really independent visualizations. I'm not going to show this, but it was quite surprising. The robot is accurate to about 100 microns, or better than 100 microns, over quite a large range in displacement. So you can very accurately control the velocity and speed, and also for more complicated motions than just this linear acceleration. Okay, so we ended this visualization. Okay, so let's see what the result was. So here at the bottom you see the profile for the velocity. So we do a constant acceleration, and then we have a constant velocity until we get to the other side of the tank. And we did this for different depths. And here on the top panel you see the actual measured force. Of course, we had some noise, but that was clearly electronic noise. And we also got these frequencies which were around 17 Hertz. And these were associated with the shedding of vortices from the edges of the blade. And what we see here is, well, when we start the plate, there's a kind of step response. The blade deflects, and the mount of the blade deflects a little bit. Then we get a sort of like increase of the force until we reach a certain maximum force. Then when the velocity becomes constant, the force decays a little bit, and we see sort of like 2 peaks, which could be associated, we see that later, with sort of shedding of vorticity, separation of vortices from the blade. And so once we reach a sort of steady state here at the end, we could determine the steady state drag coefficient in this case. Lift doesn't play a role for this type of flow. Okay, so then we get this result for the steady drag coefficient. So that's all the way at the end as a function of water depth. And so here is the water depth. So this is when the top of the blade touches the water surface, and this is basically the position that rowers are being taught at the start. So keep the top of your blade at the water surface, because you don't want to put the blade too deep, because you have to do a lot of vertical motion with the rowing oar. So this is the depth, and remember again that the height of the blade is 100 millimeters. So when the blade is just sitting at the top or just partially submerged in the water, then we found that the measured drag coefficient is actually comparable to the drag coefficient of the flow over a fence. Yeah, so about 1.1. And then when you're very deep into the water, so far below the water surface, so from about 120, 130 millimeters below the water surface, we also find a more or less constant value for the drag force, or the drag coefficient, sorry. And this corresponds to the flow behind a fully submerged rectangular plate, a drag coefficient of about 1.3. But then to our surprise, we found that if you submerge this plate, 100 millimeter in height, about 1/5 of its height, so at 20 millimeters, the drag force is actually about 60% higher than this position over here. Yeah, and then there's a dip, there's another, sort of like almost like another peak, and then before you get to this fully submerged value. So we do get quite an increase in efficiency, because then the slip velocity would be lower. You can accelerate the boat faster. And so my student, who was being second with only 700th of a second, by putting the blade in at the right position in the water, you could gain already at the first stroke in the rowing contest. And this can actually very easily be implemented. You can trim the blade so that its natural position is about 1/5 of its height below the water, or otherwise you can just put a marker on the oar so that you get it in the right position. And so this is a very easy gain that can be easily applied in rowing. Okay, so this was one part. That's the steady phase. But the other part is the acceleration part. And that was also quite interesting. So what you see here, this is the time, just in dimensional units. And then we have different accelerations. And here we accelerated to the same terminal velocity of 0.3 meters a second. And so, of course, the light blue is, it takes a much longer time before you reach that value. And when we increase the acceleration, you reach that point faster. And the dots that you see here is basically the added mass force. And what we did here in this graph, of course, the force that you measure, you have to subtract the mass or the force to accelerate the blade itself. So the mass of the blade times the acceleration. Then we also subtracted sort of what the terminal velocity friction coefficient or drag coefficient with the velocity squared. So that for long times the remaining force term would basically go to zero. And then we have these terms over here. This term is the added mass term, which would basically be constant. So if there would only be like in an ideal fluid, you would just go up and stay at a constant value for the force, and then you would lose this term and you go back to zero. And so this is the conventional for added mass term. And then this term over here represents this linear increase. Now, of course, during the acceleration phase, the acceleration is constant. This is just a time shift that gives the linear term. So this additional force would be due to an entrainment of mass into the wake. So the amount of mass that you have to carry along. This would be like a non-ideal fluid added mass term, so to speak. And so we call this the hydrodynamic mass combined with the added mass. Okay, so of course, when you see something like this, you try to find out what is the scaling. You see when the acceleration increases, the force increases. And what is quite interesting is that the actual maximum force that you have at the end of the acceleration phase is about 2 to 3 times higher than the added mass term. Yeah, so during the acceleration phase, you can apply much larger drag force than what you would expect based on added mass alone. And there it became a little bit interesting, because if you go to the literature, what should you do if you have instationary flows? For example, Maury-Gariep introduced this dimensionless time scale, this formation time, which you got from looking at the flow separation of a ring vortex generated through a nozzle. And that's basically then the integral over the velocity in time divided by a length scale. And here we would take the height of the blade, and this 100 millimeter. So if we do this, yeah, then we get indeed this dimensionless time. And what I should have noticed, well, I can go back in this experiment. What is of course interesting is that the terminal velocity is the same everywhere. Yeah? So at the moment that you stop the acceleration, all these different experiments have the same Reynolds number. So basically, this experiment does not scale with Reynolds number. And so we should really look for a different type of scaling. So then we got to this scaling based on this formation time. And but the interesting part is the data only collapses for the section where there's no more acceleration. And so we get a very nice collapse where the flow is not really dominated by this acceleration phase. So where we have this acceleration, the data do not really collapse. And it also appears to scale in a nonlinear way with the acceleration itself. Yeah? So if we basically go from 0.41 to 0.82, it seems as if this force is about 2 times larger. But it does not really appear to be proportional. And we also don't know what appears if you would accelerate beyond 1.6 meters per square second. And so this is still an open question. And so we're continuing this research to find out how this scales. But our principal interest was to look at the effect of water depth. And essentially, the presence of the surface changes a little bit the arrangement of the vortices that are being generated at the edge. And so at the 20 millimeter water depth, there's a very strong flow going over the blade, and this sort of changes the flow a little bit. And how fluid is being entrained. And what we see here, I can maybe start it again. Okay, here it starts again. Oh, I have to hit it. Yes, of course you can see these first these tip vortices being generated, and but you can already see quite early some change in the development. On the right panel, we show in the upper and lower half the total circulation in the blade. And approximately at about formation time of about 5, we start to see that part of the vorticity is being shed. And here, in order, we get the the amount of optimal part in the drag force. So here we see indeed that's much larger amount of vorticity is being shed compared to this one. And here, up till the end of the motion, the total wake appears to be attached to the blade. There's not much shedding of vorticity, and that coincides with also the higher force that we see in this position, and this optimal water depth. Okay, this also has implications, for example, for ship motions. If you have a rudder or other objects below a water surface, that there can be quite a difference in the effective drag force that you have. Yeah, so the immersed value does not apply. Okay, so this was about the starting stroke, and so now we go to the actual rowing stroke. And so this is basically if the rowers are at sort of mid race, where they row at a constant speed with not too much headwind. The purple curve you see here is the motion of the blade tip in the water. So we recorded this from a bridge, and then we had to put this into our robot and then look at the sort of like more complex motion of the blade. Okay, so here you see the different parts. So the total stroke is about 0.1 seconds. So we normalize everything between the start of the motion where the blade hits the water. We call that the catch, up until where we take the blade out of the water, which is then the release. And we could digitize this path and program it into the robot. And robots are designed to move from one point to the other. They don't care about speed and about acceleration. So you have to, but in our case, we want to pre-program the velocity as well as the acceleration of the blade. So that requires just a few tricks in order to make that work. But we managed to do that. So this is again motion of the blade. Here are the positions, the horizontal and the vertical positions of the blade itself. Okay, we programmed that in the computer, and again, what you saw a few slides back is that the flow appears to be quite two-dimensional. So we have a light sheet going in this plane through the blade, so approximately halfway through this blade. Again, we put with a mirror, we look from the bottom up into the flow. Light sheet comes from two directions, so we have no shadows because this blade was not transparent. And then we move the blade in the same manner through this in this tank. Okay, so here you see, sort of the vorticity that's being generated. I don't know if this one repeats. And then at the end, the blade is moved out of the water, and we can again see these two counter-rotating vortices at the end. I think I don't. Okay, and start it here again. Yeah, we didn't draw in the blade because at this time it was a little bit proprietary what the shape of the blade was and or how we arrange the blade, but I can show that a little bit later. And again, these measurements are repeatable to a very high degree. Even the details of these vortices are quite similar. Okay, so then we have to analyze this. Well, normally in conventional, let's say, aerodynamics or hydrodynamics, you have a force and you define a drag force or a lift force with respect to the constant velocity in your wind tunnel or in your towing tank or in your water flume. But of course, here the velocity and the direction is continuously changing. And so if we measure a certain force over here, the question is how do you analyze that? So what you could do, for example, is, well, as a fluid dynamicist, you would like to know a drag force, so that is tangent to the trajectory of the blade, and you have a lift force which is normal to this trajectory. Or you could say, well, I have a normal force because this is the force that the athlete applies to the blade. And there is then another force here which pushes sort of the rowing oar against the rotation point, which is a loss term. Yeah. So, and of course, most relevant to the rowing is this force in the direction where the boat is supposed to move. Yeah. So this is like a useful force, and this normal force, which is normal to the length of the boat, that's a loss term. Yeah. So there's different ways how to analyze that. And also because the velocity is continuously changing, and also the direction of velocity is continuously changing, a definition like the classical definition of a drag force and a lift force with respect to a reference velocity is becomes a little bit shaky. So instead, what we did to analyze the motion is to look at the total impulse that the blade is generated. Yeah, so this is just the integral of the force over time between the catch and the release, and this gives us a vector of the total amount of momentum basically that has been transferred from the blade to the fluid. And we'll use this later to optimize the motion and the configuration of the blade. Okay, so now here's a little bit. You saw the movie before, so now here with the blade drawn in with the PIV vectors at a lower resolution. So just after we got the catch, yeah, the blade is basically moving outward. So the flow occurs almost parallel to the blade. So we generate a shear layer on both sides of the blade. If you go a little bit later, yeah, so this is up to 1/3 of the total rowing motion. If you go a little bit further, then this vortex here has grown into a leading edge vortex. We can see here some trailing vortices in the wake of the blade. And in this case, the motion of the blade is basically in the opposite direction as the motion of the boat. This is the moment just before the release. Yeah, so we sort of have a larger distributed vortex over here. It's no longer like a single leading edge vortex. And then this is a little bit after the blade has been taken out of the water. And then the vorticity here on one side of the blade has formed into this second vortex, and here we have now a counter-rotating vortex pair. And what you can see if you compute for this situation, this impulse vector, you can see that this impulse vector is equal to the direction at which this vortex pair continues to move. And for a typical rowing stroke, the one that we investigated, this occurs at about a 15-degree angle with respect to the motion of the boat. And so part of the motion is useful and part of the motion is not useful, because this momentum is generated normal to the motion of the boat. Okay, so let's have a little bit more detail. So we defined all these force components. And you can basically consider that with respect to this dimensionless time between the catch and the release of the motion. And here we have the different components. So the one that is most relevant to rowing is this Fx force. That is this green force, because that is generated in the direction of the boat motion. Here on the right, this is basically the same data, but now plotted as a function of the angle between the catch, which is at about minus 50 degrees, up to the release of about plus 25, almost 30 degrees. And again here, maybe here's better visible. So Fx is what we are interested in. And then you can see that, that this force is basically almost identical to the drag component, and this lift component. So and then as we progress, but you should notice that this blade is continuously rotating. Yeah, so at one point the lift force becomes negative, but this occurs at an oar angle around 0. So then the blade has moved in the other direction, and you would have to flip the sign of the drag force, of the lift force, and of the drag force. So so this is essentially what we have to analyze, and it appeared that a little bit better way is to now decompose our drag and lift forces with respect to the boat motion. So I think it's better to look at the right graph here. So now we still copied the drag and the lift forces that we measured, but now we consider only the contributions of the drag force in the x direction and the contribution of the lift force in the x direction. So you have to look carefully. So Fx, that's a solid black curve. That's the one that we have over here. That's the force that contributes to the propulsion of the boat. And then we can see that in the beginning, let's say the first part of the rowing motion, that the drag force contributing to Fx is basically very small, and then starts to increase when we almost, of course, the blade is at 0 degrees, or basically 90 degrees with respect to the direction of the boat. And so during the first half of the stroke, the contribution of the lift force to the propulsion force is dominating. That's the first part of the motion. And then, of course, the lift force is almost non-significant when the blade is furthest out, where drag dominates. And then in the second half of the stroke, we can see that the total force decreases and the lift force adds again a little bit at the end of the rowing motion. Although the sign is reversed, but also the blade has flipped in its position. So actually, the lift force makes quite a contribution of about 40% of the total contribution to the propulsion that you need. The total force, about 40% is contributed by lift, and about 60% is then contributed by drag. Okay, now here's as an illustration, you can interpret that motion in various ways. On the left panel, that's just the frame that you saw before. The middle panel, we keep the orientation of the blade fixed, and then the green arrow is the direction of the flow with respect to the blade, because now the blade is stagnant. And the right panel, we always keep vertical the velocity approaching to the blade. So I can start this and you can enjoy watching it. And then essentially what you see is that if you concentrate on the middle one, is that we see an increasing angle of attack with respect to a cambered foil. Although this is not an airfoil, because the aspect ratio is extremely short. The width of this foil is only half of the chord. But you can see the generation of this leading edge vortex, and now actually the velocity reverses. So you get a stop vortex on the opposite side. And then the blade moves beyond that stop vortex. Okay, so what we essentially see here is sort of like a translating motion combined with a pitching motion. And there was this annual review of Aldridge and Jones, and they showed in this some motion of there was a simulation of a 2D blade, a flat plate, where they looked at the lift coefficient as a function of dimensions time. That's sort of dropped out of here for different pitch rates. So this is just a blade that is being translated and also rotates, and the pitch rate is K is defined here. So just out of curiosity, I tried to see, okay, how does this compare to our rowing blade? So our rowing blade would have a pitch rate of about 0.5, which is also shown here, also 0.5. And this is, of course, for a 2D profile or 2D plate. And then our blade actually has same qualitative characteristics. You see here this peak occur. They define this formation time 1 equal to the occurrence of this peak. So I also put it over here. And then you will find that after this maximum, it increases again until it reaches a maximum here by the green dot at a formation time of about 1.5. And that actually coincides quite well with this pitching airfoil. And so rowing is actually, although it's a water sport, quite well to be interpreted by in terms of aerodynamics. And also here we put the lift force relative to the lift force at zero incidence, and then you can see that it just follows a thin airfoil curve more or less, although it's of course a very inefficient blade because of its extremely low aspect ratio. Yeah, but there's quite some similarities between this numerical work of the idealized case of 2D pitching plate and our rowing blade. Just have to take a sip of water. And that inspired us, because if you realize that lift is an important characteristic of this blade, so why don't you use aerodynamic principles to try to optimize this blade? Now the student didn't have much time. But yeah, the first thing you do in aerodynamics is to change the angle of attack. Yeah, so what we decided to do is here on the lower right is to modify the angle that the blade makes with respect to the rowing oar. Yeah, so you could see that this impulse vector made approximately a 15-degree angle. So our idea is, well, what happens if we just rotate the blade with 15 degrees with respect to the rowing oar? Yeah, and then of course we can compute the total energy that is being put into this motion. Yeah, of course we don't have an athlete, so this is a little bit synthetic. But so we take the total power, integrate that over time with the instantaneous power, and then we get the total energy. And the power, of course, comes from the force times the velocity and the moment times the angular velocity. And we can look at this impulse vector. And of course, we're only interested in the contribution of the impulse vector in the direction of the boat motion with respect to the length of the impulse vector. And this defines a kind of efficiency as a dimensionless number. So if it's 1, all the impulse that you generated is also being put in the boat motion. The other one was a little bit more difficult to define. We would take this impulse with respect to the total amount of energy that is being put in the motion. Then, of course, you get something with the dimension of 1 over a velocity. And of course, everybody says, yeah, you have to multiply this with a velocity to make it dimensionless. But we couldn't really find a velocity that made sense in order to make this dimensionless. So we kept it as a dimensional unit, which is of course a little bit strange for an efficiency. Yeah, so we have an energetic efficiency, and we have an efficiency in terms of this impulse. Okay, so here are basically our results. Here is this blade angle with respect to the rowing oar. So this beta is equal to 0 is the conventional position of the blade. These are negative angles, so then the blade is moving backwards. And these are positive angles, so which means that the blade is moving forward. And this we did experiments for different values of the velocity over the trajectory, because we didn't know how it was scaling. We had to scale the velocity down with respect to the actual velocity. So we would see is our result independent of velocity. So we did 3 different velocities for our results. Okay, so this in the left panel is the result for the energetic efficiency normalized with respect to the situation for the conventional position of the blade. And then you see we get sort of a maximum between 10 and 20 degrees. So that, and then we find an increase of about 20%, which is quite significant. The same thing applies for the efficiency of the impulse. So the amount of, and this is again a dimensionless value. And then we see that the total, the full impulse that is being generated into the flow can actually be directed in the right direction when we rotate the blade between 15 and 20 degrees. And so that was our suggestion. Of course, we can implement that in the robot, And well, here we basically, I will show you the two results just right after the release. The trajectories of the blades are now slightly different because the blade with an angle of 15 degrees is moved slightly inward. So this curve is slightly different. But now we can see that we generate the total impulse in the opposite direction of where the boat is moving. So this is supposed to generate a more efficient rowing stroke, at least from the let's say blade hydrodynamics. The shape of the blade and the balance of the rowing oar is of course different, but I'll come back to that later. Okay, so yeah, there's some background sound. So I think this one goes on forever. I can bring the sound down. Then I don't know if you can hear me properly. So what we did, we built a small rowboat that could actually sail freely or row freely in a towing tank. And where we could measure the drag of this boat by measuring essentially the amount of power we put into the drive system, and then we kept the same frequency of this one, and this is just work going on, because here we could eliminate sort of the behavior of the athlete who had to deal with a different blade, with a different feeling. So this is currently under investigation. This was sort of like a spin-off student project. And we also now are performing some field measurements. We're analyzing them, where we actually had these on these rowing oars themselves. I'm not able to show you the results of that, but it appeared that at least it was possible to row with this alternative configuration. Okay, so this brings me almost to the end of my presentation. So to summarize a little bit, we achieved in constructing a robot to mimic the motion of a rowing blade in a confined volume, because the whole rowing motion takes place in a limited volume of water. And that gave us the ability to do very precise measurements with PIV and also direct force measurements to analyze the hydrodynamic forces that act on this blade. What we also found is that yeah, the optimal depth of a blade is not at the water surface, but 20% below the water surface, and that specifically applies to the starting rowing stroke. And we also demonstrated with our measurements that the lift force is actually quite important in the hydrodynamics of the blade. About 40% of the total propulsive force is being generated by lift. And I should mention here that people who design rowing blades, they don't really consider this lift. So the camber of the blade and the shape of the blade is really sort of trial and error. And then they find, oh, this blade performs quite nice, but there's no optimization with respect to lift forces, and also how you should row. Should you apply the maximum force of the athlete at the beginning of the blade, so you accelerate the blade as fast as possible to shed off a starting vortex, so the lift becomes, so you get some lift contributing, and you saw that in the start of the motion that lift is important, or if they should wait till the blade is most furthest out and then apply the maximum force. This is still under investigation. Well, then we sort of use the impulse to optimize the blade angle. So our suggestion is that the blade should be rotated by about 15 degrees. That makes the blade a little bit unbalanced. So we basically may use some smaller angles. But we're now in the progress of doing some field measurements in order to test whether or not this actually works. So some first measurements with a prototype already showed that at least it's possible to row with it in quite a normal way. And also we could verify that indeed the direction of the vortices being shed from the blade motion are now being parallel to the boat rather than at an angle. And this almost completes my talk. So what I talked about, there's one paper in 2019 about the accelerating blade in JFM, and just a few weeks ago, our second paper, the second half of this talk, was accepted, so that will soon appear in JFM if you want to read the details of this research. Now, at the beginning of this presentation, I showed you my former PhD student, Arnoud, who was very upset because the Italians won. And just, well, in the meantime, 2 years ago, his follow-up team got a revenge because here the Dutch team beat the Italian group, sorry Francesco, but they beat the team with 2 boat lengths. So they got their revenge. And this was still with conventional blades. Let's see what happens in the future if this type of optimization is actually being used in rowing, and even more, just then changing the sort of the angle of attack in the motion. You could also try to optimize the blade shape itself, so that lift and drag are being optimally used during a rowing stroke. Okay, this Francesco, this completes my my presentation. So I'm open to answer any questions.
So first of all, thank you, Jerry, for the very interesting seminar, and yeah, for sure, the stage is open for questions. So just feel free to unmute your mic if you want to ask a question, and or you can write it in the chat.
Yeah, I would like, Peter Fels, hello. I enjoyed it very much. Thanks for the talk. First of all, I was an oarsman myself, a rower myself, so I feel how it is being in a boat. And some years ago, I wrote a paper about rowing. And in our paper, we considered the kinetic energy within the fluid after the stroke. Have you considered that? And I found that a quite nice measure for the efficiency, since this kinetic energy is lost and it influences then the efficiency, the propulsion efficiency of the rowing.
Yeah, but I think if I go back, yeah, I think that I was not aware of your paper, so Cam notified me about your work. I also know that Arthur Veldman in Groningen has also worked on that, so I have to go back a little bit. Sorry, do one thing at a time. So our optimization here, I think this term would be comparable to your term, because this is the kinetic energy that is being transferred from the basically from the blade to the water. Yeah, so this is what the athlete puts in, and what we try to do, and I have to go back to this one. Oh, it's a little bit of a mess. To this one is that just the energy itself is not enough. You also have to see where this kinetic energy is being directed. So you need this this impulse in order to see if also the amount of momentum being transferred to the water is in the opposite direction of the boat motion. Because this component here, this Fy normal to the boat motion, maybe that was not clear. So the boat motion is so the boat motion is in that direction. So this force here is a complete loss force.
Yeah, yeah, I like that very much. Thanks. And was nice was that entrainment force. I wasn't aware of that force. I always thought of drag force and added mass, but that entrainment, that was new for me. Thanks for that.
Well, it was also very new to us, so I use it. So now I use it to get an ERC project to further investigate this, because this is also of relevance to boat motions and motion of ships and offshore structures. I think also to what Lex Smits talked about a few months ago, fish locomotion, where if you have an accelerating motion, that the actual forces being generated, hydrodynamic forces, can be larger than purely on added mass itself. So the classic added mass, yeah, maybe I'm cutting corners, but if you look at the literature, the added mass as it was defined by von Karman basically a long time ago for impulsive motions, has not really changed very much over the year. And when I talk to people in maritime technology, they still use those concepts to look at motions of large structures. But yeah, I don't know. Maybe the incident at the Suez Canal was a sudden motion. And it could be that, well, maybe it just went to a shallow part of the canal, but yeah, if you make a maneuver, then maybe the forces can be quite larger, and then you can get some unexpected motions of a large ship. So that is our interest. I want to know how you scale this, because so far I haven't really found a good way of scaling these forces in accelerated, strongly accelerated motions, and also continued accelerations. So for short times, added mass works perfect, but for elongated motions, yeah, I have not found a proper scaling yet. But that's the idea of the research project.
Yeah, thank you very much.
Thanks, welcome.
Yeah, Jerry, I also have a question. So, if I understand correctly, you know, yeah, this high lift force at the beginning is really what we also know as dynamic stall, no? And it's used also in a number of applications. But it sounds to me like, you know, the blade comes out of the water before you get the bad part of the hysteresis, so to say. But and this is something we also look at: pitching, plunging, airfoils, etc. And among other things, depending on the situation, it can be that the chord is one of the scaling factors. You know, how strong and how long does the leading edge vortex persist? And my question is, are you completely free in designing the blade, or are there some constraints on the blade from, you know, regulatory bodies, and say, well, you can't make it longer than this, or a larger aspect? Because I mean, there is work that tells you sort of, you know, how to how best to make the airfoil.
It appears that my student Arnoud, who was one of like a top rower, he's actually the technical committee of the Dutch Rowing Association, and that also has to do with the technical aspects in an international level. And he told me that the rowing blade is free. The boat itself, you cannot, because when he started to do his PhD, he wanted to modify the surface of the boat just by compliant coatings and everything. But that is not allowed. So they're not allowed to put riblets or any other structure on the boat, in the hull of the boat. And also the motion of the athlete, because if they would sort of like push off, if they would sit in a fixed location and just push off, then they can generate a larger force. That's also not allowed. But the blade appears to be completely free.
Yeah, then I think there's a lot of potential there.
Yes, yeah, but what I've seen, for example, the people who design these blades, for example, they hear about vortex generators and that you can prolong stall and everything. But then they put these vortex generators on a little ridge. It makes them completely inefficient.
Okay.
And the rowers themselves, they know, because they take off these vortex generators again and row with a normal blade again.
Yeah, sure.
So now we have been doing some tests to see if you can actually row with this blade. It's the same with this with this skates with the hinges in it.
Yeah.
Some skaters can work with it, others not. So this is still working.
Okay, but the work on pitching, plunging airfoils, we've been working this for quite a while, and now we know the scaling for the strength and the duration before a leading edge vortex detaches. And so, I mean, you can use this information then to.
That's why I put in the graph from Eldridge's paper.
Yeah,
because you can see exactly the same things. Sure. The only thing that I haven't really seen yet is with respect to these accelerating motions, and basically also with a non-constant acceleration. So that's what I'm.
Yeah, this is much more complicated. It is clear. Yeah.
Is there any other question? So is there any other question in the audience? I think
David Simmons.
Yeah. So
it's in the chat.
Yeah, it's in the chat. Yeah.
Okay. In the phase where the oar enters the water, and how is best to initiate the stroke to get optimal coverage over the blade? Would you say the optimum entry would be to match the X velocity of the blade? Yeah, we have not. So thank you for your question. We have not looked at that aspect yet. Of course, when you do this in an uncontrolled way, then you get an enormous splash, and I think it's evident that that is a loss of energy. I think if I also listen carefully to both of my students who are very good rowers, is to enter sort of because the blade has a certain velocity, but you have to move the blade if you're rowing in the opposite direction, so that you don't splash too much water, so that it just enters vertically, and then you have to start to accelerate. And so I wouldn't bring it into the water at an angle, but just going straight in. That would be something to investigate. Our current robot could only do 4 degrees of freedom. So this would require a 5th degree of freedom. So we're working on a small research project together with our colleagues at Aeronautics. So with Fulvio, who was a couple of months before me, to add an additional degree of freedom on this robot. So then we could also test the entry of the blade into the water. But so yeah, I think that's a very good question, but we have not investigated this aspect, and also of air entrainment into of the blade when you enter it into the water. Jacques, I think I see Jacques raise his hand.
Yeah, Jacques, please go ahead.
Thank you, Jerry. What is your interpretation about the optimal depth for the drag phase, the acceleration phase? You have an optimal depth of 20 millimeters of the blade.
So basically what happens if you have the blade touching the surface, you get a sort of like half a elliptical vortex, and then if you have it very deep in the water, you just get like an elliptical vortex that is the shape of this blade. When you're a little bit below the surface, you get sort of like a mixed situation. But what you get is that there's a very strong jet that goes over the blade, and that creates like a high velocity jet going over the blade. And it might be that this will generate a vortex or behind the blade, so that might cause an extra a little bit lower pressure behind the blade that contributes to a higher drag coefficient. So that would be that is what we could see in the flow visualizations. Of course, the direction of the PIV plane was normal to that, so we couldn't see that vortex in our measurement. But also the wake itself stays more attached to the blade itself to have this higher drag force.
Yeah, because we worked on the interactions of disk wake and the wall, and we see this intermediate regime where you have a flux of momentum between the disk and the wall that is blocked in the recirculation region. That is, and I think that your increased drag could be maybe explained by this kind of momentum transfer.
We also looked at, because we also did some research on swimming, where because people look at finger spreading for swimming. So we found a few years ago, well, that was already known that if you have a slight spreading of your fingers, that you have a higher drag coefficient. And that is basically, that's what we showed. That's Betz or Bates theorem. I learned in German it's Bates, not Betz, Bates theorem. And so our initial thought was that if you have the blade touching the water surface, that it is a mirror blade on the opposite side of the water surface. So if you have a slight opening, then you would get, you can just apply the Bates theorem and compute the higher thrust that you have generated. But that appeared not to explain this case. So it's much stronger than just this effect.
I think that your idea of entrainment could also, because this generates a very significant interactions between the jet that enters the separated regions and the shear layers that is coming from the other side of the blade. So I would guess that this would generate a much higher entrainment. This might explain your observation of a much higher unsteady force.
But okay, but this is a very small jet, so you entrain in the jet, but it's a confined jet then, with respect to a free surface.
Okay, so thank you very much.
So I'm not sure what's really happening at that moment.
I will try to send you some information later. So
yeah,
thank you very much.
I appreciate this. That would be nice.
Thank you very much.
Okay, so is there someone else who would like to ask a question? Once again, feel free to unmute your mic or to write in the chat.
So, Francesc, maybe notification because I should leave my building in about 15 minutes.
Yes. I just may ask a last question myself, if it's fine with you. So, if you come back to the very last, and I must admit from my side, painful slide, we see actually that there are cases in which rowing can be applied also like fluid mechanics applied to rowing, can include the case in which you are paddling in the wake of another. So how would you expect this optimization change when basically you have multi-row boats or canoeing? Or
well, first of all, because that question was asked before, because when you have more than one athlete in a boat, and especially if they're with two oars, then does the vortex generated by one rower affect that of the next stroke? But these strokes are really completely separate. So the boat, between strokes, the boat advances much more than the position of these vortices. So it's not that Ken was referring to pitching airfoils, and there you can have this effect that sort of like the shed leading edge vortex still contributes when you move to the other side of well, an oscillating airfoil, like for insect flight, where one shed vortex still interacts with the wing. So that's not the case for rowing. rowing behind each other. Yeah, the wake of the boat itself is of course extremely small. This is such a the drag coefficient of these rowing boats is extremely low, and they barely generate a wake. So being in the wake of the boat itself will not help you. So in a race where they're not in lanes but freely on a river, I don't think there's an advantage of rowing in the wake of another boat. I don't really think that that is the case because of the extremely low drag coefficient of the boat itself.
Mm-hmm.
I don't know if that answered your question.
Yes, totally. So I think, well, I don't see anyone else raising his hand for asking questions. I don't see any other question in the chat. So I would say let's thank our speaker again. Thank you, Jerry, for the very interesting presentation of today. And I hope to see you all next time, and wish you a good evening. Thanks again.
Okay. Oh, everybody, thank you for your attention, and hope we can meet in person soon.
Thank you.